Throughout this pandemic, my family has been getting groceries for my elderly neighbor, as she couldn't go herself due to risk of contracting COVID. Moreover, there are many other people, such as those with certain disabilities, who are unable to get their groceries in person. This led to our problem statement. Those unable to shop in person, either due to COVID or disabilities, need a way to shop for groceries during the pandemic because going to the store in person puts them at risk. Our solution was to create an AI, artificial intelligence, powered shopping cart that, when told which item to look for, can navigate a grocery store to find the desired item. This cart could help people shop without going in person. It could also aid existing programs like Instacart or be a feature of specific grocery stores, but the major accomplishment would be removing the need for a human to do the shopping. After interviewing experts in AI, we realized that our project was very ambitious, so we needed to simplify things. We came up with the following attributes for our cart. It follows a line along a single aisle, where we chose the shelves by the Discovery Center Cafe to be our aisle. It stops at each item, takes a picture, and uses a neural network, which I'll explain later, to determine which item it sees. It takes input from a user for which item to look for and keeps navigating the aisle until it finds that item, and it has an arm to grasp the item and place it into the cart. Moreover, to make our life easier, this arm would work for only one type of item, namely a can. Unfortunately, we were unable to complete the arm, for reasons to be explained later, but we were able to create a final product that meets all of our other requirements. Now to an explanation of our process.
Because we were all separated for most of the project, we're going to go over each of our low, mid, and high fidelity portions of the project. Harry and I initially were working together for the low fidelity part of the project. While Harry was looking at motor control, I was looking at wiring and how to connect the hoverboard motor to the Raspberry Pi. Through research after 2 weeks, Harry and I were able to order the parts we needed, and we were able to connect the motors to the Raspberry Pi. However, since we were both remote at this point, we ended up splitting up for the rest of low fidelity. For the rest of my low fidelity and for mid fidelity, I worked on the line following algorithm for the robot. In low fidelity, I used Python to make some simple test code that I could use as an outline during mid fidelity. And then throughout mid fidelity, I polished and finalized the code, but I wasn't able to test it until the shopping cart was fully built, so it ended up having some bugs that we had to fix later. The line following algorithm uses line sensors we attach to the bottom of the shopping cart. These line sensors detect colors, so the line sensors would simply output a 0 or a 1 if it's on a dark, non-reflective material or if it's on a light material. The code I made would use these outputs and tell the robot to turn off one of the motors so it could turn back to the line when one of the line sensors noticed that the robot is on a dark surface.
So, my name is Harry Akins, and my low fidelity action plan was proving control over one motor with the Raspberry Pi. And so, after all the connections were secure, I hooked it up to the Pi and began testing. And the motor worked fine, and I had control of its direction when stop started, but I did not have control over the speed, which is something I hadn't realized at the moment. So, after the low fidelity action plan, my mid fidelity action plan was connecting the second motor and basically building the rest of the robot. I did the exact same thing that I did for the first motor on the second motor, but this time it was much faster because I had some experience. So after the second motor was up and running, we needed to find a suitable base. We figured buying a disassembled cart would be better for our project, so we needed one that was sturdy and had enough height to see or grab stuff from the shelf. And this red one fit our needs. So once it arrived, I got to assembly. The back swivel wheels were taller than the motor wheels, so I needed to give the motors an inch or two of height gain to level things out. The motors also cannot be directly attached to the sheet metal of the cart, so I decided to use wood to attach the motors and give them some height. So after I assembled the cart, I needed to attach the line sensors. These needed to be close to the ground to get proper readings. I made a simple attachment to add to the bottom of the cart and attached the line sensors about 2 inches apart, which is the width of the line we'd be using. Then I drilled a hole through the middle of the cart for the wires to connect to the pod.
The focus of my low and mid fidelity work was creating the neural network for our shopping cart. Neural networks are the basis of most artificial intelligence. They are mathematical models based on an animal brain that help a computer learn how to perform a task. A convolutional neural network, or CNN, is a specific type of neural network that looks at images of objects and classifies them. CNNs learn to associate an input image with an output, a recognized object. CNNs are given a large data set of annotated pictures, which are images labeled with the correct object they depict, that it learns on. If trained properly, a CNN can generalize to correctly match images it has never seen before with objects that it's already familiar with. During my low fidelity, I learned how to code in PyTorch, which is a framework within Python for coding neural networks. I learned how to create a convolutional neural network with PyTorch and used it to write test code for our neural network. Of course, I left space for changes or additions that would have to be made. Then, during my mid fidelity, I updated the test code from low fidelity. I added code to import a dataset and adjusted hyperparameters in architecture. Basically, that last part just means that I customized our neural network to better fit our specific task. I also worked with Harry to plan how we would connect his part of the project, the robot, with my neural network.
For the high fidelity portion of the project, I worked on the robotic arm. During high fidelity, I had many issues. Since I was remote only, I was unable to help my group members, and they couldn't help me. Initially, to speed up the process of building a robotic arm, I thought that we would be able to find an arm online that we could order and build, but all the arms online were too small and required a lot of motors and battery power. Then I thought that I could try to build an arm using parts from school. Although this was possible, finishing this by myself in just a few weeks wasn't feasible. Not only did I have to build an arm, but I had to find a way to connect it to the Raspberry Pi and code the arm to pick up cans for the shopping cart. Thus, my group and I decided to scrap the robotic arm. However, I still researched it and found a design similar to the one I would have built. The robotic arm would have a reach about 2 feet so it could grab cans from the shelf. The arm would work similarly to a crane, picking up the can and dropping it in the car at different angles.
So for the high fidelity action plan, I was allowed back in school and it was time to merge what we'd all been working on. So first I set up and drilled in a mount that holds the tiny Pi camera. Then I tested the cart's line following capabilities on the line at school. The sensors were too high at first to get any readings, so I lowered them with washers and then tested it. The cart was pretty successful, but tripped up on darker rocks within the floor. Then at school, we gathered data. At first, we took 25 photos for each item, and then AJ trained the neural network on that data.
Eventually, we were able to run the neural network on the Pi and print what it thinks it's seeing. The first time we tested it, it was not very accurate and labeled everything as soup, so we had to get more photos. But this time we put a white background behind the cans to lower the contrast and get more detail out of the cans. We also got 50 pictures of each item this time, and as a result, the accuracy greatly improved. To fix the issues with the rocks, we placed white paper on the floor, and it fumbled a lot less after we did that. We're very satisfied with our final product, although if we had more time, there are a few additions we'd make. The most important would be to build and attach a grabber arm, take even more pictures to train the network on, especially with different lighting to improve performance when it's darker out, and to possibly add more items and aisles to work on and navigate through. Anyway, here's a video of our robot looking for and finding the can of pineapple.
Here we can see the cart moving along the black line. It stops at each marker when both sensors read black. Then it initiates the camera, gives a preview of what it's seen, and prints which can it thinks it sees. If the can it currently sees matches the user input can, then it stops. If not, it keeps searching.